If you take a normal ball bearing, slice through the outer segment and then reassemble it, something really interesting happens. To explain, let me start from the beginning. The concept of the ball bearing is actually very simple. It has an inner ring, an outer ring, and a bunch of spheres which are sandwiched between those two rings. These balls are held in position by a cage. So, in theory, when one ring rotates relative to the other ring, there's very little friction because everything rolls. This, by the way, is a ball from an enormous ball bearing previously installed in a now decommissioned wind tunnel. Anyway, ball bearings have a fundamental limitation. If we push the inside of a bearing relative to the outside, it has a bit of wobble. That's because it's impossible to manufacture something with an absolutely perfect fit because, well, this is the real world and nothing is perfect. And by the way, for this demonstration, I'm using a special high clearance bearing to exaggerate the effect, but the effect is still there with any bearing. The solution is to apply opposing axial forces to the rings to take up the wobble. In engineering terms, this is called a bearing preload. But here's the problem. It might sound simple, but you can't impose that force without then impeding rotation. So if I, for example, use a spring to apply that force, I'm having to apply an opposing force here with my fingers, which means as soon as I let go of the spring, the preload disappears. If I put a nut on the shaft to keep the spring compressed, and I mean shaft in the loosest possible terms because it's really just a bolt, the force is now no longer going through the bearing balls, and so the bearing remains wobbly. If I dish this washer to contact only the outer raceway, then when we tighten up the nut, the preload goes through the balls, but then the bearing can't rotate. Instead, you're left with no choice but to take two of these bearings and stack them together. If you put a spacer between the outside of the two bearings, you can apply an opposing force to the inside rings of the bearings to eliminate that wobble. But then you need space for two bearings in your structure, and you need a way of applying that preload. This can get quite complicated, especially when you have to consider the effects of thermal expansion, because as the structure or shaft expands and contracts, the bearing preload can change surprisingly dramatically. This is something my dad, Alistair, and I have been discussing for quite some time. And is it even possible to make a bearing that has zero wobble? Well, the answer is yes. The first thing we have to do is dismantle a bearing, which is a bit tricky. We start by popping off the seals. These prevent the ingress of dirt when the bearing is in use. This is actually very easy to do though, so the first real challenge is with the cage, which is usually riveted in place. But we found these bearings which have crimped cages, so we can pry them apart with a scribe. Once the cage is removed, the balls can then be pushed to one side of the bearing to allow us to dismantle the remaining pieces. The clearances between the balls and the cage are very tight because it's made to be assembled by a robot and then never come apart again, so it does require a hefty push. Once it's been taken apart, it looks like this. The outside component of the cage can then be mounted on a grinder to cut it into two pieces. At this stage, the bearing can be reassembled. Actually, reassembly is much easier than disassembly because the balls can be popped back into the cage first. So what exactly did we achieve here? Well, upon reassembly, the bearing works in the same way. Yes, there's some of the outer race missing, but in the case of an axial load, that part of the ball bearing raceway doesn't see any load anyway. But here's the beautiful part. By simply applying the force to the outer raceway, we can now preload a single bearing. Hopefully you now understand the theory, but does the principle actually work? To find out, we tried fitting this bearing into Alistair's milling machine. Like the majority of machine tools, this table is traversed by the feed screw engaging with a nut. When the screw is rotated, it pulls or pushes the table. In this case, the ends of the feed screws are each supported in normal ball bearings. Before we fit the split bearing to the y-axis, this is how much the handle rotated without translating the table. It's between 0.1 and 0.2 millimeters. That means this system has that much backlash. Minimizing backlash is desirable for certain operations, such as climb milling, so wouldn't it be nice if this could be reduced? With the new bearing fitted and preloaded using a shim, you can see a huge improvement, with the backlash now measuring around 30 to 40 microns. The action is lovely and smooth, and there's even a noticeable improvement to the quality of cut from the machine with the new bearing fitted. We originally came across this concept when scrutinizing the manual for my Schaublin cross slide. Looking at the cross-section diagram in the manual, this too seems to use the split bearing concept. After a bit of research, the closest type of bearing you can buy seems to be called the 4-point contact bearing, but I'm not clear on whether these can be preloaded, so perhaps someone can enlighten me in the comments. This is the high clearance bearing I showed earlier in the video, which is designed specifically for high-speed applications to allow room for that thermal expansion issue I demonstrated earlier. I ultrasonically clean this bearing to remove the factory grease, and look how long it spins for. This is what the same bearing looks like straight out of the packaging. It seems that completely stripping the factory grease improved it. Now, if I put a drop of even low viscosity oil in the clean bearing, it seems to come to a complete stop. If we do the same thing between two flat metal surfaces, we get completely the opposite behaviour. Isn't that weird? When you think about it, both systems are seeing metal on metal contact, so why is it that the sliding block behaves in exactly the opposite way to the bearing? And should we be running ball bearings without lubrication? Let's start with explaining the metal block situation. When the two metal surfaces are in contact, all the little microscopic lumps and bumps in the metal surfaces cause friction. But when a drop of oil is added, it forms a film that keeps those surface asperities separated, and so the friction reduces. This is called hydrodynamic lubrication, and if you get the right balance of viscosity for a certain sliding speed and load, you can get a very low friction. This can be demonstrated on the Strybeck curve. You can see as we progress along the x-axis, different lubrication regimes arise. The lowest friction occurs when the lubrication film is just thick enough to keep those asperities on the two surfaces separate, but not so thick that the viscous forces impede sliding. So why is it we don't see this with the bearing? Well, I think it comes down to the fact that the balls are rolling. Because rolling produces such little friction, as soon as the lubricant is added, the viscous forces dominate and the bearing slows down. Okay, so now I hear you ask why bearings come pre-greased. Well, so about 10 seconds ago when I said ball bearings roll, I lied. When bearings are subject to a load, the balls and the raceway actually squash ever so slightly. It's imperceptible to the human eye, but it's enough to cause sliding at a microscopic level. So, should you run lubrication in your ball bearings? In the vast majority of cases, yes, you absolutely should. But in low-load applications where minimizing viscous drag is a consideration, and fidget spinners come to mind here, then perhaps you should try removing the factory grease. I would like to say a huge thanks to our patrons. Without you, making videos like this one just wouldn't be sustainable. And thanks to all of you who watched this video to the end. I hope you learned something interesting. I'll see you in the next video.